Okay, so now we're going to work with confidence intervals, but instead of working with proportions, we're now going to work with means. So we're going to estimate a population mean, which means we have to record values of now we're working with a quantitative variable for a sample of individuals. So just to remind you of what we talked about from chapter 3, the shape of our sampling distribution, we have the normal condition from the central limit theorem. Either our original sample is normal, which means our sampling distribution is normal, or our sample size is large enough, meaning greater than or equal to 30, so then the sampling distribution is approximately normal. We also have that the center of our sampling distribution should be our mean of the mean of the sampling distribution should be the same as the mean of the population. And then we have our spread, which is the standard deviation of the population divided by the square root of n. And that's true as long as we meet that 10% condition. So we can only use that if we meet the 10% condition or if we meet the independence. So either the probability doesn't affect each other, we're sampling with replacement, that would give us independence. So now we have the one sample z-interval for a population mean. So that's our test. That's what it's called. So when we do our 4-step process, we're going to say one sample z-interval for population mean. What we're going to try and do is we're going to estimate this is good to estimate our mean when standard deviation is known. So I don't know the mean of the original population, but somehow I know the standard deviation of the original population. That's when we can use this. And so that formula looks very similar to our formula for proportions. Instead of the proportion, we have the mean of the sample, plus or minus our z star, and then times our standard error. And our standard error for means is standard deviation of the population divided by the square root of n. And again, this can only be used when we meet the normal condition. So either our original population is normal or our sample is greater than or equal to 30. And to be able to use that standard deviation, we also have to make sure we meet that independence condition. Problem is this isn't useful because usually if we don't know the mean of the population, we don't know the standard deviation of the population. So this really is no good to us because we don't know that standard deviation of the population. So what do? Well, we can use this to work with margin of error. So now we're going to be looking at choosing a sample size for a population mean. So if we want a certain margin of error, what size should I use for my sample? So even though that is not helpful for calculating our mean, it is helpful for choosing the sample size. But it requires usually a pilot study to help us give a standard deviation to work with. So then we're going to calculate a critical z-value from our normal curve table or from a calculator. And then we're going to go ahead and use this formula right here. Z star times that standard error has to be less than or equal to the margin of error. So here's our sample problem. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate the mean at 90% confidence level with a margin of error of at most 30 minutes. So here's our margin of error. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. So now here's our standard deviation. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30 minutes? So the first thing we need to go ahead and talk about is what is our z star. So we're going to go ahead and do an inverse norm. And the area is going to be, leftover area is 10%, and we want half of that for our tails. So this is our area. Our mean is 0, our standard deviation is 1. And this will give us the z star. And when we calculate that on our calculator, we're going to get a z star of 1.6449. And they already told us that our standard deviation from a previous pilot study is 154. And we know our sample size is, oh, that's what we want. We don't know. We don't know sample size. But we do know that we want margin of error to be at most 30 minutes. So we're going to go ahead and plug into our formula, margin of error. We have our standard deviation, the square root of our sample size, which we don't know the sample size. That's how we're going to figure it out. And then we're timesing that by the z-star 1.6449. So what we can do right now is we can go ahead and multiply these top numbers, 1.6449, and we get times 154, we get 253.3146 over the square root of n is less than or equal to 30. Then what we're going to do is we're going to move up that square root of n. So I multiply by the square root of n on both sides. So that way this cancels out with that. And then I have 253.3146 is less than or equal to 30 square root of n. So now I divide by 30. And I get 8.44382 is less than or equal to the square root of n. And I want to get rid of the square root, so to undo the square root, I'm going to square both sides. So that'll cancel out that square root, saying that my n has to be greater than or equal to that 8.422444382, which is 71.298 about. So if my sample size has to be bigger than 71, then I need at least 72 students to have that margin of error based on that pilot study. And so that's what we can use that formula for. Now, we're going to talk about what happens if you don't know your mean, you don't know your standard deviation. Well, we can use the z-score formula, standard deviation of a sampling mean, along with the substitution of the standard deviation of our sample. And then all of a sudden what happens is now this turns into this. And just by substituting that with the standard deviation of our sample, we get this new distribution, but the new distribution is not normal. It looks normal when you glance at it, but it truly isn't normal. In fact, it has longer tails. And if our sample size ends up small enough, it may end up looking like a mound. So here is the distribution with the where n is less than 30. We have here is the distribution when n is close to 30. And then here's the distribution, the normal distribution. So see how with the more people we get, it gets closer to that normal distribution, but it's not. And so the less people you have, the more it kind of mounds out. And the more people you have, the closer it comes to a standard normal distribution, or the z distribution. So each distribution looks different depending on the number in our sample, and we call that degrees of freedom. And so the number, how many people are in our sample, will determine our shape of our distribution. And so we need to calculate a degrees of freedom to figure out what that shape is. Now, t-distributions are symmetrical. That is important to know. They are single-peaked, and they are bell-shaped, but again, they're going to have a larger spread than the normal distribution. The larger spread comes from the substitution of the standard deviation of the sample, which introduces more variation than the standard deviation of the population. And that is just enough to make it not a normal distribution. So as degrees of freedom increase, the t-density curve, or that t-distribution, will approach the standard normal curve more and more closely. So What are we going to do with this? Well, we actually have tables for t-distributions. And in fact, our calculators, you know how they have an inverse norm? They also have an inverse t, because we have programmed in there the t-distributions into our calculator. So, information you need to know to be able to use the t-distribution, and that is degrees of freedom. There is a really complicated formula for degrees of freedom, and we're not going to use that. We're going to use the simple, safe version, and that is the degrees of freedom is our sample size minus 1. And so our distribution will be a t-distribution as long as the sampling distribution is close to normal. So we still use a normal condition for our sampling distribution, because as long as sampling distribution is close to normal, then our t-distribution will apply to our sample. So we use that to kind of help us out. So let's look at our table. Using a table B, so table B, table A is our Z table, table B is going to be our T table. Suppose you want to construct a 90% confidence interval for the mean mu of a normal population based on an SRS of size 12. What critical value T should you use? So right away, if my size is 12, then my degrees of freedom should be 12 minus 1, which it is important that you write that down. It's 11. So I know that my degrees of freedom is 11. And then I look at my upper tail probability. So what is the area? If it's 90%, that means I have 10% left over, which means there's 5% on each tail, which means I'm using that. The nice thing about the t-distributions is it tells you the confidence level at the bottom. So this is a 90% confidence level, which means that the area is 0.05. And then this is something really cool for those of you who don't like to use your calculators or want to use your tables. It tells you z-stars for those confidence intervals right there, which is really nice, unless you're doing something like a 92% or 93%, which isn't in there. But it gives you the more common confidence intervals that we use. So if I'm doing 90% degrees of freedom 11, my t-star is 1.796. How to do it on the calculator? Just like we do inverse norm. We do second vars, which is our distribution menu. We go down to option number 4, which is inverse t. And then we do area, just like we did area for inverse norm. And then we put in our degrees of freedom and hit enter. So here, this would be an inverse t. My area would be the half of 2% left over, so 0.01. And my degrees of freedom would be my sample size minus 1, so 21. And when I calculate that, I'm going to get an inverse t of 2.5176. So now inverse t, area is 10% left over, so 5% on one side. And degrees of freedom would be sample size minus 1, so my degrees of freedom is 9, which gives me an inverse t of 1.8331. 95% confidence interval, so interval t. Area is 5% left over divided in half, 0.025. Degrees of freedom should be 6. And that gives us an inverse t of 2.4469. Okay, so let's move on. We've talked about the inverse t. So now, how is our confidence interval going to look? Well, it's going to look just like our confidence interval before, except for now we have the standard deviation of our sample instead of the standard deviation of our population. So just slightly different, but because we're making that substitution of the standard deviation of the population, this is now called a one sample t interval. So when we're calculating intervals, we're going to be using t intervals. We use this only if the population is normal or the sample size is large and the population is at least 10 times as large as the sample. So we still have the independence condition. We still have the normal condition, and we still have a random condition, because random means that we can take our results and apply it to our original population. So, just like I said, our conditions for inference, we have random, we have normal, and we have independent. Okay, so our sample problem, and again, this is a 4-step problem walking you through everything. So you should always, this is a free response. I typed up a lot of stuff for you, but this is all stuff you should do. You need your state, you need your plan, you need your do, you need your conclude. So you should be putting all of that in there. So can you spare a square? As part of their final project in AP Statistics, Christina and Rachel randomly selected 18 rolls of a generic brand of toilet paper to measure how well this brand could absorb water. To do this, they poured 1/4 cup of water on a hard surface and counted how many squares it took to completely absorb the water. Here are the results from their 18 rolls. Construct and interpret a 99% confidence interval for mean number of squares of toilet paper needed to absorb 1/4 cup of water. So what are we going to do? We're going to estimate the mean amount of toilet paper needed to absorb 1/4 cup of water with 99% confidence. Okay, what are we going to use? We're going to use a 1 sample t interval to estimate our mean mu. We're going to check our conditions, and yes, I spelled conditions wrong, but that's okay. So we have a random sample of 18 rolls. Normal condition is 18 greater than or equal to 30, and it's not. So it doesn't meet the normal condition that way. But we do have a caveat. If our original population is normal, then we're okay. So now what we have to do is we have to check for normal by graphing this data. And so we can graph it as a histogram, but then we have to do all sorts of calculations. We could graph a dot plot, but again, we have to do calculations to check our empirical rule. The best way to do this is by using a normal probability plot. So what we're going to do is we're going to take our calculator, we're going to put these in list 1 in our calculator, and then we're going to go ahead and we're going to do a stat plot. We're going to go to the last graph on the stat plot, and we're going to graph our list 1 on the x-axis and go ahead and see how that looks. So let's go ahead and grab my calculator. Okay, this helps if I turn it on. So there's my calculator. I'm going to go to Stat, Edit, and there's all my numbers for my list. So now I'm going to go into my stat plot. I'm going to turn on my plot. We're going to come down to the very last graph. We're going to use L1. We're going to graph it on the x-axis, and then hit graph. And if you can't see it, we do zoom 9, and that allows us to see our graph. Now, based on our graph, it looks pretty linear, which means it's approximately normal, and that's what we're looking for. Is it approximately normal? Now, because we are proving to people that we could do this, we need to actually sketch that out. We need to show them that it's approximately normal. So we're going to go ahead and we're going to sketch out this graph really quick. We've got dot, 2 dots, 2, 1, 2, 3, 1, 2, 3, 1, 1, 2, 1, 1, 2, 3. And then we say, since it is pretty close to linear, or pretty close to a straight line, it is approximately normal. And so now we've just taken care of the normal condition. So now we're going to go to independent condition, and we can say, you know what happened, how much one roll of toilet paper, how much water is absorbed by one roll of toilet paper does not affect another roll of toilet paper. So water absorbed by one roll does not affect water absorbed by another roll. So these are independent in nature. So now we're going to use our calculator to calculate x bar, sx, and t star. So to calculate x bar and sx, we need to do a one variable stats. So we go back to our calculator, we hit stat, we go over to calculate, and we do one variable stats, and we find that our x bar is 24.9444. We find our standard deviation is 2.8588. And then we calculate inverse norm. Not inverse norm, inverse t, because we're doing means. And then our area is 99%, 1% left over, half of that is 0.005. And our degrees of freedom, well, we had 18 rolls of toilet paper, so degrees of freedom is 17. This gives us an inverse T of 2.8982. So now we're ready to go ahead and calculate our interval. We start with x bar, 24.9444, plus or minus our T star, 2.8982, times our standard deviation, 2.8588, divided by the square root of our sample size, 18. So in our calculator, we times this and then divide by the square root of 18. We end up with 24.9444 plus or minus 1.9529. When I take the 24.9 and I subtract the 1.95, we end up with an interval of 22.9915. Then I add that to my point estimate, so now I get 26.8973. So there's my interval. Now we have to go ahead and interpret that. We are 99% confident that the interval from 22.99 to 26.90 captures the true mean number of toilet paper squares needed to soak up 1/4 cup of water. And we are done.